Alright everybody, in this video I'm going to be going over the exponential and logarithmic models unit tests that we took last week. Part 1 starts by asking you to identify whether a model represents exponential growth or exponential decay. And then to get a 4, you should be able to write a function that describes a pattern. Before we start with number 1, I want to actually refer you back to this packet. Something that we learned in this packet is that the general form for an exponential function is y equals a times b to the power of x, where a represents your initial value and b is the constant multiplier. And then we also learned that if b is a number that is between 0 and 1, and you have to say both of those things. It is not enough to say that b is less than 1, because that would imply a negative number, and that's not what we're talking about. It has to be a number between 0 and 1, and then that would represent exponential decay. And you can logic your way through it. Think about like the number 20. If you multiply 20 by a number that is between 0 and 1, I think the easiest one to think about would be 0.5. Well, 20 by 0.5 would be 10. So your initial value is decreasing when you multiply it by a number that is between 0 and 1. However, on the other hand, if you multiply your initial value, in this instance 0.25, by a number that's greater than 1, in this case 2, then your initial value is going to start out there, but it's going to keep increasing. So this would represent exponential growth. And then in both cases, the y-intercept will be 0, comma, whatever the initial value is. Why? Well, the 0 is your input, right? If you input 0 for x, anything raised to the 0 power becomes 1. So all of this becomes just 1. And 12 times 1 is 12. And it will always be the case whenever you input 0 into a function like that. So here it would be 0.25. Oh, actually, and then if you scroll further down on this packet, remember we did the activity with Gabriel and Brandon borrowing $1, and then that's actually how we discovered Euler's number, which we learned is approximately 2.71828. The way that you get Euler's number is if you take the limit of n as it approaches infinity of 1 plus 1 over n to the power of n. So take your calculator, make n be 1,000,000, make n be 7 billion, make n be the biggest number that you can think of. At some point, it stops mattering what huge number you put in. You're going to get 2.71828. Okay, so all of that to take us back into our test. The initial value here is 0.4, and the constant multiplier is e. And e is 2.7, or approximately 2.7, which is a number that is greater than 1, and therefore this would be exponential growth because a constant multiplier is greater than 1. And you need to use all of that proper vocabulary if you want to get a 4. If you take a look at example 2, your initial value is going to be 4. So the way to get the initial value is notice what happens when your time is 0. You have 4. When nothing has happened, you start at 4. So we know that our function is going to be y equals 4 times something to the power of x. We know what the constant multiplier is, but let's analyze this table a little bit more. We know that as our x values increase, our y values are decreasing. So therefore, this might be exponential decay. We still have to prove it. Well, I don't know what 108 divided by will give me 36. But I do know that 36 divided by 12. Sorry. Divided by 3 will give me 12. And I know that 12 divided by 3 is going to give me 4. And I know that 4 divided by 3 is going to give me 4 over 3. And I can feel confident now that 108 divided by 3 is going to be 36. And so it looks to me that the constant multiplier, be careful, it's not going to be 3, but it's going to be 1 over 3. And then logic your way through it. Is your initial value 4? Yes. Is your constant multiplier a number between 0 and 1? Yes. So it does make sense that your table, the y values are getting smaller as the x values are getting bigger. And then in this portion, that's where you would explain that the table represents exponential decay because your initial value starts at 4, but as the x values increase, your y values decrease. You can even get more in depth by saying what the constant multiplier is. Okay, part 2, expanding and condensing logarithms. I think the biggest mistake that I saw some of you make is that you forgot to put the 6 under its own logarithm. So this would be log base 7 of, log base 7 of 6 plus log base 7 of a to the 3rd power plus log base 7 of b to the 4th power. Most of you joined the 6 and the 8 together, and that's where you lost credit. Remember that you don't stop there. You can turn the exponents into a coefficient. So it will look something like this: log base 7 of a plus 4 log base 7 of b. And then this would be your final expansion. And here you are doing the opposite. You are condensing. So you have log base 8 of z plus another way of writing this down, and I try to help you out before your quiz or before your test to remind you that another way to write this would be as 1/2 times log base 8 of x plus 1/2 log base 8 of y. Okay, and then we notice that all of the terms are being separated by addition, and so we are able to join the arguments by multiplying them together. So it's going to be log base 8 of z times x to the 1/2 power times y to the 1/2 power. And then I didn't take any points off you, but the expectation, or what I was hoping for, is that you would notice that anytime that you have an exponent of 1/2, it's like taking the square root of something. So if you have the square root of a times the square root of b, since they have the same power, you can join them together into a single and put both of those values into a single radical. So the square root of a times b. So in here we could do z times the square root of x and y. And then that would have been your final answer. 3. This is not directly expanding and condensing logarithms, but it is a skill that helps you be able to do problems like number 4 better. So we have something in terms of y and z, and then something in terms of y, s, and z. We're being asked to rewrite s in terms of z. So this is my hint. That's my hint that I need to take that variable and isolate it. So I start out with y squared equals s over 2 times z to the 3rd power. How can I get rid of this fraction? How can I make it so that I'm no longer dividing by 2z to the third? Well, the inverse operation would be to be multiplying by 2z to the third. And whatever you do to one side, you do to the other, right? So now we have this. We have that s is equal to 2 times z to the third power times y to the second power. But they're telling us to rewrite s in terms of z. And at the moment we have s, but it's written in terms of z and y. And we can't have any y's. But that's when this guy comes into play. So what we're going to do now is we're going to rewrite the whole equation. But instead of having my y, I'm going to go like this. Instead of having a y, I'm going to substitute for the value of y. And I know that y is equal to 4 times z to the fifth power. And then we're going to expand that. So we have 4 squared is 16, and 5 times 2 is 10. I'm using the power rule here. And then all I have to do is now multiply everything that I can multiply together. 2 times 16 is 32, and I'm going to make use of the product rule here, so this will be z to the 13th power. Number 4, if log of 5 equals b, then express log of 2500 in terms of b. This is your hint. This is what you look at. How can you make it so that you can express this number as having a base of 5? Well, you go like this. Log of 5 to the something power. And I have these zeros at the end, so I know that it's going to be times 10 to the something power. I should be able to figure out what exponents go in those blanks such that when they multiply out, I get 2500. Okay, just looking at this part, I know that 5 to the second power is 25, right? But I don't need 25, I need 2500. So what am I going to do? I'm going to multiply it by 10 to the second power, which is 100. Okay. Since they're being multiplied, I can separate these by adding them together. So log of 5 squared plus log of 10 squared, or log of 100. What does that become? I can expand this a little bit more so that it's 2 times log of 5 plus, oh my gosh, what's log of 100? Log of 100 is just 2. Why is log of 100 2? Well, the invisible base here is 10. So essentially what a logarithm does, its sole purpose is to find a missing exponent. So 10 to the what power is going to give us the argument, right? That number is going to be 2. And that's always the answer. The exponent is the answer to a logarithm. So log of 100 is 2. Okay. Anyway, look at this. We have a log of 5 here, and we have a log of 5 there. What is log of 5? Log of 5 is equal to b. So instead of writing log of 5, I'm just going to write the letter b. And then bring down the plus 2. And then you're done. We have expressed log of 2500 in terms of b. Part 3. Okay, there's 2 ways of doing it. I think I might show the way that I think most of you did it, which is that instead of writing a 1, you wrote 4 to the 0 power. Or at least you should have written 4 to the 0 power. Why? What's 4 to the 0 power? 4 to the 0 power is just 1. So you didn't change the equation, you just changed what it looked like. Okay, we're going to make use of the quotient rule here. Because our bases are the same, we can use a quotient rule. And so we have 4 to the power of 6x minus 4x plus 2. And we're going to set that equal to 4 to the 0 power. Okay, now that our bases are the same, we can set the exponents equal to each other. So 6x minus 4x, and then this is where I screwed up, minus 2 is equal to 0. Some of you forgot to change the 1 to 4 to the 0 power. So instead of having a 0 here, you had a 1, which threw out the entire equation. Okay, so 6 minus 4 is 2x minus 2 equals 0. Now you add 2 to both sides, and you have 2x is equal to 2. And you divide by 2 on both sides, and so x is equal to 1. Okay, here most of you got that you were supposed to do plus 4 on both sides, and so now you have 2 to the power of negative 8n is equal to 16, and then for some reason you died. There's two ways that you can do this. The easiest way, I think, is to rewrite 16 as 2 to the power of 4. Rewrite that number as a number that is base 2. Okay, now that the bases are the same, we can set the exponents equal to each other. So negative 8n equals 4. And if you divide by negative 8 on both sides, you'll get negative 1/2. Oh, I don't like what that looks like. So negative 1/2. Okay. The other way of doing it is that once you get to this portion right here, instead of rewriting it as 2 to the 4th power, you could write, okay, log base 2 of 16 is equal to the exponent, which is negative 8n. And log base 2 of 16 is equal to 4. So 4 is equal to negative 8n, and then you still get that n is equal to negative 1/2. So no matter what option you choose, you still get the same answer. Okay. At this point, you may have noticed that you don't know how to evaluate logarithms in your head. So in other words, if I give you something that looks like this, log base 5 of 125, and you don't automatically know that that's equal to 3, that is your hint right now to stop this video and go Google how to evaluate logarithms in your head, or how to solve logarithms, how to evaluate logarithms. Okay, here we are going to make use of our properties of logarithms. Since we're adding the logs, we're going to multiply the arguments, and we will have log base 4 of x times x minus 6 is equal to 2. If we expand, we'll have x squared minus 6x is equal to 2. And then, bam, I died. And that's at the heart of everything that we've done in this chapter. Once you are dead in logarithmic form, convert to exponential form. This no longer works for us because we have an x, right? So what we're going to do is we're going to rewrite it in exponential form. What is your base? 4. What is the exponent? 2. And we're going to set that equal to the argument, x squared minus 6x. Okay, 4 squared is 16. And then this is a quadratic equation. And when I'm solving quadratic equations, one of the first things that I want to do is make it be equal to 0. So I have to not add 16, I have to subtract 16 from both sides. And so I have 0 is equal to x squared minus 6x minus 16. And I'm going to hope that I can factor this. Let's see, what two numbers multiplied together give us 16, but added together give us 6. I know in my head that the difference between 8 and 2 is going to be 6. So I feel like those are the numbers that we're going to end up using. And then negative the 8 would be negative and the 2 would be positive, and bam, it looks like this works out. So x is equal to 8 and x is equal to negative 2. And then you didn't get a 4 on the rubric if you didn't account for extraneous solutions. So if you put negative 2 into this term, you will have an undefined solution, and so you can't have negative 2 as a solution. So you have to reject it, and we've only accept that x is equal to 8. Okay, number 4. Here we are subtracting logarithms, right? So we're not multiplying them together, we're going to divide them. So we have negative 3x minus 1 over 7 is equal to 2. And same thing as that other problem we had. The logarithmic form no longer works for us. If we put this into the calculator, even if we could put it in a calculator, nothing would happen. So we're going to turn it into exponential form. What's the base? What is the missing subscript? It's e. You know that it's e because you have the words ln. So e to the second power is equal to negative 3x minus 1 over 7. And then you're going to multiply both of the sides. Oh, yeah, wait. In your test, some of you took the square root on both sides and you said, well, e is equal to the square root of negative 3x minus 1 over 7. That doesn't work because you're not solving for e, you're solving for x. E is a number, remember? E is about 2.7. So we have to multiply both sides by 7. And then we're going to add 1 and divide by negative 3. So x is equal to 7 e to the second power plus 1 divided by negative 3. And then you still have to check to see whether you will have an extraneous solution. I know that 7 times maybe, let's round this up to 21. 7 times 3 equals 21. And wait, no, that doesn't work because, okay, imagine that that's a 3. So 3 to the second power is 9. And 9 times 7 is 63. And 63 plus 1 is 64. And 64 divided by negative 3 is going to be a negative number. And then, okay, so imagine we substitute a negative number here. A negative 3 times a negative number will be a negative number. So a negative number times a negative number will be a positive number. And even if we subtract 1, it'll still be a positive number. So we can be sure that this is a real solution and not an extraneous solution. Okay, number 4. Either you were here the day that we learned how to do this, or you weren't paying attention. But this one is not too bad. We learned that a parent function is a function that has no transformations. It's extremely basic. There's no shifts to the right or left. There's no up and down shifts. There's no vertical stretch or compression. It's just the parent function. So we have log base 2 of x, and that's it. I think the majority of the class got this right, but then graphing it is where you died. Okay, things that you should know as Algebra 2 students. Things that you should know as an Algebra 2 student is that a first degree function, when you graph it, is going to look like a line. A second degree function is going to look like a U. A third degree function is going to look like an N, or potentially it's going to look like an N that's stretched out a little bit too much. You should also know that when you have a 4-degree function, you're either going to have a very fat U, or you're going to have a W shape-ish graph, or when you have an exponential function, it's going to have an asymptote at y equals 0, but it's going to grow very rapidly out of hand. Think of COVID. It grows really fast. And then the opposite is true for a logarithm, or the inverse is true for a logarithmic equation. You still have a function that is growing, but it's growing extremely slow. And its asymptote is at x equals 0. So it'll never go beyond this point. But it doesn't grow fast. It grows very, very, very slowly. Okay, so now that you have everything that an Algebra 2 student should know about graphing things, we can look back at the parent function and identify, okay, well, the shape is going to look something like that, right? It's going to, this is what the graph's going to look like. And then you can make yourself maybe a little table to help you. And this is why I told you that if you didn't know how to evaluate logarithms, that you should pause the video and go look it up. Okay, let's start with some easy values. If you substitute 0 into x, so if you have log base 2 of 0 is equal to what? Well, think about it backwards. 2 to the power of what number is going to give you 0? Nothing raised to the anything power gives you 0. So 0 is going to be undefined. Okay, so scratch that. Now think, log base 2 of what number is going to, of 1 is going to give you, sorry, I worded that poorly. Log base 2 of 1 is going to be equal to 0 because 2 to the 0 power is going to be equal to 1. So when your input is 1, your output is 0. The next easiest number to plot is going to be the base, which is 2. So log base 2 of 2, that's the same thing as asking 2 to the what power is going to give me 2? Well, that would be 1. So when your input is 2, your output is 1. Okay. Usually it's enough if you have those points. You could keep going if you want to have a little bit more exactness into your graph or make it look better. You could do 3. So log base 2 of what is going to give you 3? That doesn't work. But 4 will work. 2 to the what power is 4? 2. So when your input is 4, your output is 2. Okay, let's make this what's another power of 2? 8. 2 to the power of 3 is 8. So when your input is 8, your output is 3. And I think we have enough values to start making our graph. So at 0 is undefined, but we have a point at 1, 0, and we have a point at 2, 1, and we have another point at 4, 2, and 8, 3. And then we know the shape of the graph is going to look like this, and bam. Okay, and then we can just count each of the puntitos and look at how the transformations affect them. So if it's plus 3 inside the parentheses, we're actually going to be moving to the left. So we're going to take this puntito and what the heck? We're going to take this puntito and we're going to move it 1, 2, oh, no, sorry. We're going to take that one and we're going to go 1, 2, 3, and 2 down. 1 and 2. So 1, 2, 3, 1, and 2. We're going to do the same thing for this one. So 1, 2, and 3, and then 1 and 2 in the bottom. 1, 2, 3, 1, 2. 1, 2, 3, 1, and 2. And then if the original parent function had an asymptote right here at x equals 0, then the new asymptote of the transform function will actually be equal to x equals -3 because you're moving everything to the right 3 units. So all in all, when you graph your new function, it will look like this. And then you would write the asymptote. X equals 0 and x equals -3. And be careful to make sure that you understand that these match, that this is a parent function and that this is a transform function. Okay?